Suppose we wanted to design an experiment to see if caffeine affects pulse rate. We'll do this in class to talk about the different aspects of experimental design. So here's an idea. Everyone measures their initial pulse rate, then everybody drinks some caffeine, we wait for a little time, we measure the final pulse rate, and we compare final and initial pulse rates. Well, what are some problems with this plan? Well, there may be some other things that affect pulse rates besides just caffeine. Maybe what people did their last class period, maybe they're anxious about their next class, maybe their overall fitness level causes their pulse rate to stay fairly steady, all kinds of things. People may have different reactions to caffeine too. Some people drink a lot of caffeine, so maybe drinking more doesn't really affect them much. Some people, maybe the body size or weight affects how much caffeine affects someone. So we want to look at how to design an experiment so that we can be reasonably sure that any change in pulse rate is based only on the caffeine. So first of all, it's important to have a comparison group. In the way this is set up, we're just comparing before and after. So what if, for example, everybody in the group gets so excited about the amazing stats lecture I'm giving that all their pulse rates go up? Well, we wouldn't know if that was their pulse rates went up because of the caffeine or because of the amazing stats lecture. So the amazing stats lecture and the caffeine would be confounded with one another. So the way to combat that is to include what's called a control group. The purpose of a control group is to give a group to compare the treatment to. So the control group receives either no treatment or what's called a placebo treatment. It's a fake treatment, and they are compared then with the group that does receive caffeine. So that's what I did in our experiment. All students drank a Pepsi. One Pepsi, though, had caffeine in it, and the other Pepsi did not have caffeine, and they were in plain paper cups, so students didn't know which one was which. So the control group was receiving no caffeine in this case. So if their pulse rates all went up for some reason, we could still see if the ones that got caffeine had a different increase in pulse rate than the group that didn't have caffeine. Let's just examine some of the vocabulary about experiments. An experiment has a treatment or treatments, which is a specific condition applied to the individuals in an experiment. This is a variable or combination of variables that are deliberately manipulated by the researcher. So in this case, I was deliberately manipulating whether students got a caffeine drink or no caffeine drink. The experimental units are the smallest collection of individuals to which a treatment is applied. So for example, if you randomly selected a classroom, the experimental unit would be a classroom. But I individually randomly select individual students in my class. All my experimental units are my AP Stat students. Usually if we have human experimental units, we call them subjects in the experiment. The factor is the explanatory variable. Sometimes there's more than one. It could be multi-factor. Here we just had caffeine. Sometimes the explanatory variables have more than one level. So maybe if I'd given some students a certain, 10 grams of caffeine and another student other students got 20 grams of caffeine and other students got no caffeine at all, that would be different levels. But in this case, it was just one level of caffeine. Now, there's three other things we want to do when we design an experiment. We want to make sure that the two groups, the caffeine and non-caffeine, are as similar as possible and are treated in exactly the same way, except for the fact that one got caffeine and one didn't. So to do that, we randomly assign the subjects to the two groups. We know that there's going to be a lot of individual variability between people as far as their pulse rates, their fitness level, their activity level, their reaction to caffeine, all sorts of things. But if we randomly assign them to groups, then that ensures that the effects of those uncontrolled variables are balanced as nearly as possible among the treatment groups. It is essential to always randomize, since there will always be other variables we cannot control or that we do not consider. So if someone says, but what about this variable? You can say, it doesn't matter. I randomly assign subjects to treatments, So those should be fairly, that particular variable should have equal effect in both groups because I randomized. How do we randomize? We randomize by the ways we've done with the sampling. We random assignment, we use a hat method, we use a random number generator, we use a random digit table or something along one of those methods. Now notice, we are not randomly selecting a sample. We don't do any sampling in an experiment. Usually experiments with people involve volunteers. We randomly assign our subjects to treatments. That's where randomization comes in an experiment. In a completely randomized design, all of our experimental units or our subjects are in one group, and we apply the randomization process to all those individuals and divide them into our treatment groups. In this particular experiment, I numbered my students 1 to 10 and used my calculator, which is a random number generator, to generate 5 different numbers from 1 to 10. Notice I said different, no repeated numbers allowed. And the 5 students chosen drank Pepsi with caffeine, and the remaining students drank Pepsi with no caffeine.